Good day everyone, I am Cuenca, a BSE CE 3A student, and today I will discuss to you the impedance matching and one of its method, which is the quarter wave transformer matching. So let's get started. Here are the topics to be discussed. First, the definition of impedance matching. Second, the importance of impedance matching. Next, the derivation and application of quarter wave transformer. And lastly, since this is a laboratory subject, I will show you the simulation of impedance matching using quarter wave transformer as a matching network. What is impedance matching? Impedance matching is defined as the process of designing the input impedance and output impedance of an electrical load. In this transmission line figure, suppose that ZO is not equals to ZL. But in this impedance matching, we create or design a matching network so that we can transfer a maximum amount of power to the load. What is the importance of impedance matching? First, maximum power is delivered and power loss is minimum. Second, impedance matching improves the signal-to-noise ratio of the system. And lastly, impedance matching in a power distribution network will reduce amplitude and phase errors. Consider a transmission line having a characteristic impedance ZO and a load impedance ZL. We all know that if ZO is not equals to ZL, this will result to mismatch impedances. In these mismatch impedances will result to some fraction of voltages that will reflected back to our source. And it is according to the reflection coefficient represented by gamma L, which is equal to ZL minus ZO all over ZL plus ZO. We can understand it better with this illustration. This red wave is the standing wave. Here, mismatched impedances throughout the circuit yields a high voltage standing wave ratio. High voltage standing wave ratio transfers a minimum amount of power from the load to the source. Standing wave represents power that is not accepted by the load and reflected back to the feed line or into the source. In addition, this blue wave is the incident wave distributed to our load. Since ZO is not equals to ZL, there will always be a reflected wave represented by this green wave. As we can see, if we compare this amplitude of this incident wave, we can see that it has a power loss and its amplitude has been decreased. And take note that in mismatched impedances or in mismatched network, it transfers a minimum amount of power to the load, as we can see in this illustration. This is only the distributed voltage. Moreover, our goal here is to have a maximum power that is transferred to our load. Here, we just add a matching network so that we will introduce to a new input impedance, which is equals to our characteristic impedance, and our reflection coefficient will be equal to 0. Let's take a look to this design. This is called a quarter wave transformer. As we can see here, we just add a quarter wavelength and a matching network with a impedance which is Z1. As we can see here, here is the input impedance terminated with a load, which is given by this equation. Zn is equals to Z1 multiplied to ZL plus JZ1 tan beta L all over Z1 plus JZL tan beta L, where Z1 is the characteristic impedance of the matching network, and L is the length of the line, which is lambda over 4, and ZL is the load impedance, and beta is equal to 2 pi over lambda. Since we need beta L, we will solve for this. We will just multiply the value of beta and the L. multiplying its value, we will cancel the lambda, and this is the remaining equation. Beta L is equal to 2 pi over 4. But we can simplify it further. Hence, beta L is equal to pi over 2. Now that we know the beta L, we can substitute it in this equation. After that, I multiplied 1 over tan pi over 2 in both numerator and denominator. Using distribution property, this is the resulting equation. And take note that tan pi over 2 is approaching infinity, and any number divided by infinity is equal to 0. So it will be cancelled. So the resulting equation is like this. Zn is equals to z1 multiplied to jz1 all over jzl. I will cancel the j. So the remaining equation will be this. Zn is equals to z1 squared all over zl. But our goal here is that we want that Zn is equals to our ZO, or our characteristic impedance. So I will just substitute ZO in here. So ZO will be equal to Z1 squared all over ZL. Solving for Z1, I just multiply ZO and ZL. So Z1 is equal to square root of ZO multiplied to ZL. We will take note of this equation. Now that we know the Z1, we will solve for the length of the matching line. Take note that our length is lambda over 4, and lambda is equal to c over f. C is a speed of light, which is 3 times 10 raised to 8 meter per second, and f is the frequency. It is given in the problem. So the length of the transmission line will be equal to c all over f multiplied by 4. So recap, this is the illustration or the design of the matching network of the quarter wave transformer matching, and these are the 3 important formulas to be noted. Z1 is equal to square root of ZO multiplied to ZL, and the length is lambda over 4, and the length of the matching line is equal to C all over F multiplied by 4. But take note that all of us in this world has its own limitations, and this matching network has also its own limitation. It includes, first, the length of the matching transmission line must be quarter a wavelength. This can be true in a single frequency. And lastly, the load impedance must be purely real. This must be purely real. Okay, this is the most awaited part of my report. This is my sample problem. I will read this. A 50 ohm lossless transmission line is to be matched to a resistive load impedance ZL, which is equal to 500 ohms at 200 Hz via quarter wave section as shown in this figure below, thereby eliminating reflections along the feed line. Find the required characteristic impedance of the quarter wave transformer, and using Falstad simulation software, show the resulting graph. Suppose that the delay of the transmission line is in 2 milliseconds. Okay, I will discuss my answers to my next slides. So I'm back. I go to Google Chrome and I will search for www.falstad.com. So this is the online circuit simulator that I will be using. One of its advantages is that it shows a resulting waveform and you can visualize the output. However, it needs an internet connection. Okay, I will blank the circuit. And I will proceed to my sample problem. I copy-pasted my sample problem in this whiteboard. Okay, these are the given. Characteristic impedance ZO is equal to 50 ohms. Load impedance ZL is equal to 500 ohms. And frequency is equal to 200 Hz. I will first make a circuit diagram of this given. I will right click my mouse and I will go to inputs and sources. And I will choose add AC voltage source 1 terminal. Since I want a sine wave result in my graph, okay, I will edit its value. Here, the frequency is in 200 Hz. So I will change it into 200 Hz. And I will remain the maximum voltage into 5 volts. And I will click apply, then OK. After that, I will add a transmission line. I will go to passive components, then add transmission line. Here, the impedance or the characteristic impedance is equal to 50 ohms. So I will change its value into 50 ohms. And the delay, here it is stated that suppose the delay of the transmission line is in 2 milliseconds. There you go. I will click apply, then OK. After that, I will add resistor for my load impedance. And its value is in 500 ohms. I will add resistor. And I will change its value into 500 ohms. I will click apply, then OK. And lastly, I will add ground. So this is the circuit equivalent of our mismatch network. I will run this. And I will show you first the waveform coming from the source. So this is the waveform coming from the source. I will edit the properties of this and I will make the horizontal scale into 5 milliseconds. So there you go. Okay, I will show you the resulting waveform in this load impedance. This yellow waveform is for the current. I will remove this. This is the resulting waveform of our incident voltage going to our load in a mismatch network. But our goal here is to have a matched network using a quarter wave transformer. So we will do that. I will set aside this first. And I will add new transmission line for our matching network. Here, I will add new transmission line. And we will solve for its impedance and delay in second. Here, since we need Z1, we will solve for this. Solving for Z1, Z1 is equal to square root of ZO multiplied to ZL. Hence, Z1 is equal to square root of 50 ohms multiplied to 500 ohms. The resulting Z1 is equal to 158.113 ohms. So we will change its value into 158.113 ohms. So we need a delay. Solving for the delay in seconds, Our length here is lambda over 4, but lambda is equal to speed of light over frequency. Length is equal to speed of light multiplied to time. Substituting the value of length, we have Ct is equal to C all over F, and I copied the 4. I will cancel the C. The resulting equation is this. Time in second will be equal to 1 all over 200 multiplied by 4. So our delay is equal to 0.00125 seconds. I will click apply, then OK. Then I will run this so that we can see the resulting waveform of a matched network. As you can see, this is the resulting waveform of a matching network using a quarter wave transformer. I will stop this for a while and I will snip this so that we can compare to our first waveform. Here. This is the first circuit that I made for a mismatched network. And this is another circuit I made for a matching network using a quarter wave transformer. So here, as we compare, in a mismatched network, the amplitude decreased and there is a minimum amount of power transferred to our load. However, using a quarter wave transformer as a matching network, there is a maximum amount of power that is transferred to our load. And as we compare, this is a good design for our transmission line. So that's the essence of creating or designing a matching network so that there will be a maximum power transferred to our load and power loss is minimum. So that's all. Thank you for watching. Stay safe and healthy.